Yeah, I'll start now. So now what I'll do is that I'll try to, you know, cover some of the things which are more related to climate services and solutions, mostly in the area of adaptation and specifically related to agriculture and disaster mitigation. So we'll try to cover these things. Okay, so I'll put it in slide mode. I hope the slides are visible, right? Yes. So, I'll start with this thing because in the climate, if you look at literature, the nature science, and all these big papers, they always keep about problems. So essentially, talking about giving scary pictures and talking about problems. But one of the thing for a country like us, what we need is that how to really adapt to it. What will be the solution? That is what is more important. And the thing is same all across the sectors. It's not just climate. So I'll pick up one of the sentence which I really liked, but it was used in a different context by again the Nobel laureates Abhijit Banerjee and Esther Duflo in their famous book Poor Economics, where they said that talking about the problems of the world without talking about some accessible solution is the way to paralysis rather than progress. And I believe that this is applicable to any area and also it is equally applicable to climate. Just saying that thousands of people die, ten thousands of people will stress is not really serving the society. Of course, it gives us some information, but that may help in just getting nature or science paper, but that will not help you to progress science or progress the society. So what is important is that we have to think of a proper solution, what is coming out. So, when you're talking about sectors that need climate services, we are essentially interested in water security, food security, disaster management, health, transportation, event management, tourism, and many more. Each and every sector need climate services. The idea here is that each and every sector in today's world, we have to make sure that we are making them climate resilient, weather smart, climate ready, and weather ready, climate smart, and so on. And for that, what is needed is that we should have very good early warning system. That's number one. And number two is we should have a very good adaptation strategies that will help us to improve our recovery mechanism. So these are the things which are becoming very, very important. So now let's say if you're talking about weather and climate services implementation, one of the things which we have to understand that there has been a tremendous improvement in weather forecasting and extended range predictions in India. I would say that a silent scientific revolution have taken place in our country and of course over worldwide. And this scientific is that huge revolution is reflected if you look at our tropical cyclone forecasting. In 1999, in Odisha, we had a tropical cyclone that resulted 15,000 deaths. With the same amount of, same intensity, tropical cyclone Amphan took place in 2021, only around 100 people died. Of course, no death is really desirable, but we have to understand 15,000 to 100. So that is what is scientific revolution to me. That has very silently taken place, but we did not really give much of attention to it, but it has really taken place and it is actually saving life and it will save life in the coming future. So that is what is scientific revolution that has happened through improved meteorological science, to improve climate science, and through improved forecasting and disaster mitigation. And of course, there has been, we can see that large number of initiatives are there which are coming and extending the services to the stakeholders. But we believe that still there is a big gap between operational products and applications. Because we had an opportunity to interact with many stakeholders. Specifically at IIT Bombay, we are mostly interested in developing climate services for different sectors. And when we are looking at it, we had to interact with many stakeholders. And what we have understood is that stakeholders often are not, they do not really understand that, you cannot expect the forecast to be perfect. And if there is some error, they easily lose trust on it. So that is one of the issue which they face, and they do not understand that how to really address errors and uncertainties. Because there is always a need. if you let's say if you have developing some sector specific tool that can help you to become weather smart, then what is needed is this tool, the developer of this tool should have an idea what exactly is happening uh, on so they should have an idea that what are the specifically error structure. That's number one, and number two is that what are the problems which are there in the sector, in what way this weather forecast and uncertainties can be used to develop some kind of a decision support system. And if you have to do that, what is needed is that we need past forecast, because we need to understand the error pattern. We know IMD comes up with very good forecast, excellent forecast, but we never get hindcast from them. If you don't get a hindcast, you cannot really develop a very good decision support system tool. That's why, if globally, if you go, most of the forecasts, they also provide hindcasts. And hindcasts are important in terms of developing sector specific decision support systems, which is largely missing. Then for extreme events, you know, false alarm is another issue, and people have to understand that false alarms are expected. We cannot really avoid that. And then there are gaps of resolution, but we are now coming up with Bharat forecast system, which is super high resolution models. Probably that is helping us in that way. And process of development products. Most of the products, because we meteorologists sometimes feel that whatever forecast we are giving, we understand everything, then this will be very useful. But we also have to involve the stakeholders, so that stakeholders can understand the problems, and stakeholder also knows in what way the forecast is coming, in what way they are useful. So essentially, you have to merge all of them, and then this is one of the major limitation which I feel. Now, one of the thing is that error. If you take any forecast, any climate projections, there is an error. And nowadays, if you talk about climate model error, people say bias correction, hai na, something like that. I always make fun of it, because there is some method which is known as bias correction. Whatever model, whatever thing that will come, you just do a bias correction, then it will work. So, for example, if you look at this chain network paper of WRR, which shows the typical bias in 12 watersheds across the globe, and it shows that in what way the biases are there. These are essentially precipitation projections, and you can see that red one is the observed one, and blue ones are different climate models. Now, of course, initially when the bias correction methods were developed, the bias correction methods were mostly where we are mostly interested in removing the bias in mean and standard deviation. But in 2010, there was a group led by Professor Dennis Piletin-Meyer, and there are a few other people who have developed some method which is known as quantile mapping-based bias correction method. Now, if you look at this quantile mapping-based bias correction method, so the idea here is that if you have an observation has a specific CDF. Now, if you are taking the GCM output also has a specific CDF. You forcefully merge the GCM output CDF on the observations and change the values. That's what is quantile mapping based bias correction in a very simple language. And then what you have to do, then you need to find out future minus present historic simulation, how much changes you are getting, add that changes to it. So that's what is quantile mapping based bias correction. Since it is very easy, because you have to just fit a distribution and forcefully match it, people jumped on it, and it was used extensively in most of the climate impact literature. Almost everyone have used this kind of bias correction methods, and it is very easy. So once you have this, most of the hydrological papers, you can see that climate models have taken applied bias correction, then applied in hydrological modeling. It was so. Now the question here is that, of course, this is widely used method, but is it a very robust method? So again, this question will come. The first question, what one of our student, Vikram Chandal, who just completed his PhD, he wanted to ask is that, aren't you overcorrecting in terms of bias correction, because you are forcefully matching thing? So what he tried to do some experiment which is a bit fun experiment. So what he tried to do is that, let's say this is the observations and these are the GCM output of temperature. Then rainfall. And then what he did is that he picked up random number, just normal random number at GCM resolution. Then he applied bias correction. Look, this is the bias. After bias correction, this is the GCM output, which is matching with observations. Now, if you apply it to random number also, this is matching with observations. So essentially, if you are forcefully merging, uh, you know, forcefully merging any data to a specific data, of course, it will be very similar to observations. There is nothing great in that. But one of the issue what we are facing is that, which is very important to me, is that the initial structure of the data or initial property of the data was random, but it is totally lost now. And that is my major issue, because if you are applying bias correction, suddenly you are bringing correlation among these grids and so on and so forth, and your original assumptions is totally, or original property is totally gone, which we do not really want, because we are running GCM. We want GCS to play some role. I mean, if you are making sure that entire property is lost, then what is the point of simulating GCM? And that is one of the major questions he raised in his paper, Vikram Chandal. And Vikram also said that, when you're talking about bias means a systematic error. So bias means not just error. Now, if you look at the bias correction, if you apply this kind of bias correction, and if you pick up the corrected part, what you will find is that they are really white noise. They are not systematic error. Any error what was there, that has been removed. So essentially, you are not really removing the systematic component of the error, but you are trying to remove everything, which is forceful matching. And while doing so, further he found that you are either amplifying or reducing the changes, projected changes in a big way. So essentially, huge amplification or huge reduction is actually happening, which is another serious problem. So you can see here that, of course, this method got a lot of applications, but there are serious issues with this kind of methods. And for this purpose, we always say that we should go back to our own regional modeling or downscaling approach, which are not forceful matching, but which probably perform much better. And at IIT Bombay, we have started performing this kind of country level statistical downscaling. We started in 2013 with Ghosh and Kandan, and very recently Vikram has been working on the same thing on statistical downscaling, but with, of course, much advanced approach, where we are trying to use different deep learning approaches. We have used here YNet, of course, with some physical information, and we have found that this kind of methods are actually working well, and these methods do not have the problem which bias correction approaches have. And the most important part, what you can see, is that this is essentially active break period. So all of you are aware of what is active and what is break period. But what is important is that active and break period, they have these interseasonal oscillations, they have east-west asymmetry. For example, during active period, when central India receives very high rainfall, you can see that northeast India receives low rainfall. So there is a east-west asymmetry. Now, if you apply BCSD, you can see that this east-west asymmetry is gone, because you are forcefully merging CDS, but you are not really understanding any physics or anything. So it's actually failing. But when you're applying this sort of method like YNAD or any other methods, it's trying to capture some sort of an east-west asymmetry, which is very important. So that shows that physics guided machine learning probably helps in understanding many of these problems, rather than just blindly applying BCSD or any kind of quantile mapping-based bias correction. We have to be extremely cautious before using any kind of bias correction approaches. Now coming to agricultural thing. When you start talking about water and food security, let me tell you what exactly I feel is one of the greatest challenge India is having at this stage. India's population is growing. That there is a population growth. So if the number of people, if the population is increasing, you have to produce more food, because you have to maintain the food security. When you have to do that, you have to increase your agricultural activities. There is no way out. And when you have to increase your agricultural activities, you need more water. Now what is happening? Your temperature is increasing. When temperature is increasing, your water requirement further increases. But if you are considering availability of water, there has been weakening of monsoon, though it's reviving, but it's reviving in terms of extent. So essentially, in terms of availability, it's becoming low and demand is high. So when availability is low and demand is high, you need more irrigation. And that's what farmers are doing. They're pumping groundwater. Now this groundwater pumping has become uncontrollable. So there is no control on groundwater pumping, and that results into groundwater depletion. So what is happening every year, groundwater is getting depleted at many locations over the country. And when your groundwater is depleting, that means for extracting the same amount of water, you need more energy, more pumping, which is bad. Firstly, second thing is that is also increasing the irrigation cost. And when it is increasing the irrigation cost, this has to be reflected in some way on the crop price. And that will affect, when it will affect the crop price, it will affect the people who are not financially that good condition. For them, the food security will be affected. So essentially, to solve a food security problem, you are going back to a food security problem or food problem, and at the cost of water. So essentially, you are in a big trap, and we have to think that in what way we can come out of this big trap. And I believe this is one of the major challenge at this stage our country is facing, which is related to water. Now, one of the questions which we wanted to address is that are our agricultural crop practices really sustainable? So what we did is that we have considered three major states, UP, Bihar, and West Bengal. And what we have found is that if you consider the western part of UP, there is a decreasing trend of rainfall, but water consumption for cereals have increased quite significantly because of widespread paddy fields. And if you look at kilocalorie production per unit use of water, they are either no trend or slightly decreasing trend, which is bad because your crop quality has improved, but still you are unable to produce increase the amount of crop with per capita water use. So that's one of the major problem. And if you look at the total water consumption, you can see that more than 50% of the water used for cereal crops like paddy, wheat, and so on and so forth. So it shows that there is some problem. Now, if you look at the groundwater level, so whatever I tried to show in that flow chart, if you look at it here from here, so if you consider the western Uttar Pradesh, you can see that actually all over the Gangetic Basin, the groundwater is actually depleting, which is a bad condition. And if you do some modeling, you'll find that the models also agree. Yes, groundwaters are depleting. If you use satellite data of total water storage through this, you'll get exactly the same thing. Yes, groundwater is depleting over the Indo-Gangetic Basin. And what we are also finding is that the energy consumption is also increasing for irrigation. Not only because of more amount of water, but also because groundwater table is depleting. For the same amount of water also, your energy consumption is increasing. So, which is one of the challenging part. So, what can be a solution? So, what we thought is that, can we really ask this question to all of us that, are we really practicing the correct crop? Or what about, if we can change so we can make some changes in terms of crop. So, we are not saying that, just change everything from rice to millet, which has been claimed by some of the very recent papers, but we do not want to mention that, but rather what we would like to mention is that can we really make some changes in the crop fraction and try to find out what can be an optimum crop fraction. And for that purpose, what we did is that we tried to use some kind of a multi-objective optimization. The idea here is that can we maximize the total kilocalorie production? The second one is, can we maximize farmers' profit and minimize water use? And our constraint is that will not change the total crop area for cereals. So total crop area will remain same, only the fractions will change. So probably paddy fraction will reduce, some other crop fraction will increase, and so on and so forth. Can we do that adjustments? And since it is multi-objective, what we did is that we first solved the optimization model. So we developed this optimization model for each and every district separately. And what we wanted to do is that whenever you are performing multi-objective optimization, you have to get the best value of the objective function and the worst value of objective function. So what we did is that we solved this optimization model for separate districts separately. And from there, the base value we can easily find out when you are solving, let's say for maximized kilocalorie production, we'll get the base value for that. But for other two objective function, if you solve, among them the objective function which is giving the lowest value of kilocalorie production, that is the worst value. So that's the way we computed the best and worst value. one is most desirable, and the second one is which have to be greater than this. So in that way, we have scaled it in between 0 to 1, and we are trying to maximize. So essentially, some sort of a goal program we have used here. And when we applied that, we published this paper very recently in Nature Water, not very recently, a year back in Nature Water. What we have found is that for many regions, it is being said that the rice has to be reduced a bit, specifically over the western Uttar Pradesh. And at some dry regions, it says that millet can be increased. It doesn't say that you have to replace one crop completely by another crop, but it is trying to tell you that some optimum fractions or some management is needed. Similarly for Kharif crop as well. So for Rabi and Kharif crop, you have to make some adjustments. For Rabi crop, we have to take wheat has to be reduced a little bit. We have to increase barley and sorghum a bit, and so on and so forth. And what it says is that if you apply this kind of things, the benefits are, of course, there in terms of minimizing the water use. But the co-benefits is that sometimes when you are replacing paddy with some of the nutri cereals, we are increasing the protein index. So protein production, we are increasing 46%, iron production, zinc production, all of them are increasing. But the real challenge is how to really create demand for other crops, because we know that in West Bengal or Bihar, mostly specifically for West Bengal, people love to eat rice. And if you ask them to change it to some other crop, or at least for a few days within a week, so they will not agree. So I think how to really create the demand, that is a major challenge. How to really change the human practice, and how to really convince the farmers that yes, this is the way it will help. It will not only help you, but also it will help your future generations. So that is a real challenge, and that's a social science problem. We are not qualified enough to really solve this kind of problem, but these are really, really major challenge. So this is one of the problem which we have on which we have been working. The second problem what we are working is that how can we have a better agricultural water management, and most of this work was done by one of my students, Adrija Roy, and at present her work is now being extended to make it more implementable and more technology development and more understanding, how to couple soil moisture and everything, which is being done, which is now being I mean, one of my student, Usman, is now working on this. He's actually there at the in person in the at ICTS, and also one of my other student, Ganesh Gupta, is also working on it. So the idea here is that when you are talking about climate services for agricultural water management, we have to think of different scales for different purposes. When you started interacting with farmers, what you have realized is that, let's say for tomorrow you have to apply some irrigation. What they do is that they would like to irrigate in such a way so that in next 5 days or 7 days they don't have to irrigate. And if you have to do that, you should have weather forecast and medium range forecast to understand what are the chances in next 5 to 7 days, so that you can irrigate in correct amount. So for that, weather forecast is needed. The second important scale is extended range. That means we are interested in weekly prediction. And why do you need weekly prediction? Because in many of the arid regions, the farmers need to understand that 2 weeks in advance how much water they have to arrange. And for that purpose, extended range predictions are needed. For that, day-to-day variability is not important, but over a week, how much rainfall is expected, that is important. The third one is about seasonal predictions. For example, this season, if I am planning to go for May, I am planning to go for a water intensive crop, it will tell us, okay, if it tells that, this time, this year it says that monsoon will be bad. So then you'll be a little bit careful about, investing on a water intensive crop. And decadal to multi-decadal projections normally help us to understand if this is the correct crop for this region, or I have to think of some change. So what we tried to do is that we went to Nasik, Adrija and some of us, Professor Raghu and I, three of us went to Nasik, and we started interacting with farmers through a farm which is known as Shayadri farm, and through a startup which is known as Sensortics, which is under Shayadri. So when we started interacting with them, we asked the farmers. So I have to mention that these farmers, when we started interacting with them, we realized that these farmers, most of them are agricultural engineering graduates. They're quite rich, and most of them have installed a soil moisture sensor in their farm. So we asked them that how do you irrigate? What they said is that they check the soil moisture. If it goes slightly lower. What they do is that they consider it as a bucket. They find that how much deficit is there. They add that water to make sure that next 7 days they don't have to irrigate. But they do not consider if the weather forecast says that there will be rain or not. We told them that if you use weather forecast, it will help. They said that farm scale weather forecast does not make much sense, so we are not interested. Then what we said is that okay, we'll use it in a slightly different way. So what we said, they told them is that let's say if we have past hindcast and past observed rainfall, what we can do, we can develop a conditional distribution. Given the forecast, we can get the conditional distribution of observations. And from there, we can generate rainfall scenarios given a forecast. Now you have real-time soil moisture. We'll use a farm-scale hydrological model through Monte Carlo simulations. So you can generate a realization of hydrological scenarios. Now what we are doing, we are using a stochastic optimization where the decision variable is irrigation water application and our objective is to minimize the water application with a stochastic constant that tells you that the root zone soil moisture will be less than the water stress threshold with certain probability. And this probability can be given by the farmers. Once you do that, then you will get optimized irrigation water that needs to be applied. And when we did that, we found that farmers are able to save 10 to 30% of the water with no absolutely zero loss in yield. Of course, we filed a patent. This is now accepted. The patent is now granted. And it is under the process of incubation. And then this was also published in WRR and so on. Now, once it is being done, then what we thought is that if we have this weather forecast, in fact, when we showed it to the farmers said, okay, yes, this makes sense, this is good, but can you really help us in telling that 2 weeks in advance if I have to make water management, can we really do that? Then we started working with IITM Pune, Dr. A.K. Sahai. So we requested Dr. Sahai that can we really get the hindcast. Dr. Sahai was kind enough to provide us the hindcast. And then what we did, we considered a limited ensemble of hindcast. And with that, we used the weather generator, which is a hidden Markov model, and generated huge number of ensemble of hindcast. And then we applied this optimization method. Again, to generate farm scale eco-hydrological model with a probabilistic constant, which is 2 to 3 weeks in advance. And we found that this model is working quite well. In fact, 2 weeks in advance, we are able to produce the exact, or not really exact, but the water requirement, which is very close to the exact requirement. So that shows that, this kind of models are really working. Though the forecast at a coarser resolution, but if you somehow connect it to hyperlocal information, it adds a lot of value. At even at a very high resolution. So this is very important. And sorry. So we found that it is working well. Then the real question will come, when you need to upscale this sort of thing over a large region, let's say over a village or over somewhere, how applicable are they? And this is a real question or major question which we wanted to address. So what we did, what Adrija started doing is that Adrija used some root zone soil moisture algorithm which are already available. So what Adrija did is, so let us say if you look at this thing, normally weather forecast footprints are like this, and you can see these small pots are essentially farms, and satellite soil moisture grids are like this. So within a single grid, there are multiple points which are there. So Adrija used some method by which she could get the farm scale soil moisture, merging the whatever sensor information there, and rest she has considered the satellite information, and somehow merged them to generate some soil moisture map. And with that soil moisture map, she then applied the methods, and she found that it's actually working. So idea was like this. Let's say if you are considering a village, there are n number of farms, but you can classify these farms to same type. So this is what she tried to do. Now if you have same type of farms, you'll find that for class A of farms or class B of farms, do you have at least one farm where we have this sensor to be installed? If you have that, develop your calibrate your model with that specific farm and apply it for other farms. And that's the way she started developing. Of course, this method needs to be upgraded in a much better way, more importantly in terms of downscaling soil moisture, and then getting farmers information and then taking their information into the model and so on, which our student Usman is now working. But this was the first time where we tried to do, and what we found is that even if you do not have sensor, but if you can use nearby sensor, it serves the purpose and it works really well. And most important part is that it helps in terms of affordability. So essentially, if a farmer cannot afford, still he or she can get some good information, which was very good, and which was also our surprise, because this will add a lot of value to our to the farmers of our country. And we found that we published it in, Adway published it in Stoughton, Science of the Total Environment, and there she showed that yes, it's working quite well. Now, this is about agriculture, whatever we are doing. And second one is urban flood early warning. This is also another very important area which needs a lot of work. So, essentially, when we started working with this urban flood early warning, we started with Chennai. India's first end-to-end real-time urban flood forecasting system was developed for Chennai flood forecasting in 2015 after the Chennai flood. And this was I was fortunate to lead this team, and it has a team of 30 scientists from 8 institutions and national labs, including IISc, IIT Madras, IMD, National Center for Coastal Research, and so on. And now it is implemented at NCCI. So we'll come back to that. But before that, what I'd like to mention is that, sorry, my slide got some format issue. But what I'd like to mention is that, of course, India faces a lot of problem due to urban planning, just like any other cities across the globe. But India's urban regions also have very good system of, not really all urban regions, but at least for Mumbai, I can tell you, it has very good flood resilience. That means recovery is quite fast. Whatever extreme rainfall happens, in a day, it recovers, or in few hours, it recovers. For example, last year's extreme rainfall, for which it was not forecasted properly, but still it would recover very fast because the management system and pumping system is excellent, probably world's best in our city. Now, I'll just quickly mention that India's first real-time urban flood forecasting system, which was developed in Chennai, which is now operational by National Center for Coastal Research in the name of sea flows. And the details of the methodologies are there in this current science paper where we explained everything. The reason behind picking up current science, because this kind of methodology should be available to the Indian audience. Now coming to Mumbai. Mumbai is not as easy as Chennai. Chennai was relatively easier compared to Mumbai. And one of the first reason why Mumbai is not as easy as Chennai, because of the very high spatial variability. Mumbai extreme rainfall has very high spatial variability. For example, if you take 26 July 2005's rainfall, the Santa Cruz, this is near airport, it received 900 mm of rainfall in just single day. 900 mm, almost close to a meter. But Kolaba, which is around 20 kilometers from Santa Cruz, only receives 83 mm. So that clearly shows that how much spatial variability is there. One of our students, Supanto Pal, long back in 2018, so what he did is that he tried to run a work with multi-layer urban canopy model. And when he ran that, what he found is that, of course, he has got that in an urban setup, there will be some pockets where you receive extreme rainfall, very high rainfall, and that's why you'll get a high tail. But at the same time, what he has found is that if you consider 15-minute to hourly rainfall, you'll find every 5 kilometers the correlation coefficient drops. And if you go beyond 5 kilometers, there is not much of correlation coefficient. That shows that it actually has a very high spatial variability. So in Mumbai's flood forecasting starts with extreme rainfall forecasting. So it was a challenging problem how to really come up with a very hyper-local extreme rainfall forecast system. And we have Pooja Tripathi, who is also sitting there with you. Pooja started working on this challenging problem, and let us see what exactly she tried to do. But before that, what we wanted to tell is that, this is something, this Mumbai flood forecasting system is something where a lot of students or faculty are working together just to have a very good early warning system for the entire city. That was the purpose. Now, if you look at Mumbai's digital elevation, you can see this is the Sanjay Gandhi National Forest. This is Mumbai city, and you can look at it. This is Sanjay Gandhi National Forest, which is a high altitude area, and this is the low lying area. Now, because of this local orography, what happens? this region receives very high rainfall, this horseshoe kind of regions. Now, this is also a low-lying area. So what happens? Very high rainfall over a low-lying area. So this region gets flooded. So the idea here is that can we really capture this pattern and forecast an extreme rain? So Pooja started working on it. Pooja took the GFS forecast, global forecast system, which is of course resolution. This is from NSEM GFS. Sure. And what she did also, she tried to do some event synchronization to understand that if some of the rain stations together form a cluster or not. Sure. Once it is being done, what she did, she first applied CNN and then try to find out are we improving the GFS forecast or not. What we have found is that yes, GFS forecast is getting improved if you do this kind of downscaling, which was good enough. But when we looked at extremes, we found that improvements are not that good because these models are not doing that well for extremes. Then what she did, now she applied something known as transfer learning. She picked up that model and did further tuning for extreme events because our target is to have a very good extreme rainfall forecast. And when she did that, these are the results. What we have got is that if you consider the hit rate, that means how many times you are correctly hitting the extreme rainfall. You can see that with global forecast system that is quite low. When you are using CNN, of course, it has improved a bit. But when you are using combined, that after transfer learning model, you can see that at some of the stations, you are getting even more than 80% hit rate, which was excellent. We believe that no, it's not very easy to get such a high hit rate. But this is what she was getting. And if you look at the false alarm, you can see that false alarm was initially very high with GFS, but with this method, you can see that there is a significant reduction in the false alarm. So the model overall is performing quite well. Then what we did also, just rainfall will not be sufficient. What we also need to do is that we should have some water level monitoring because there was no water level data which was available to us. So HDFC Adway is one of the insurance company who supported us, funded us this work, and we started setting up some of the sensor locations, some of the important locations where we have put some sensors so that we can start getting the water level data. And then the other thing also we thought that, you in a city like Mumbai or any city, you cannot really have monitoring at every square inch. You cannot do that. Or every square meter or every square 100 meter or so. So you cannot do that. So what you need to do is that you have to use citizen. So what we tried to do, wanted to bring citizen science. And this was started by one of our students, Ramani Tripathi. What she tried to do is that, when we started working on this, Twitter was free. It was not like the present X. So what we thought is that can we get a lot of information from Twitter and use it? And this is the way we started working on it. But to verify the tweet, we started working with some NGOs who started. There were some volunteers who were well trained and they are also getting some information. And when we did that, what we found is that with Twitter also we are getting very good information. So normally people do not, you know, specifically during flooding, they do not give us any rumor. So essentially, most of the cases, their information is correct. The uncertainty may come the way they are presenting or the way they are looking at it, but mostly information is correct. So what we did is that last year we have developed a flood app and we did a trial run of monsoon 2024 thanks to Pooja who has been consistently generating the forecast in the last year, even this year also she has been doing that, and this year we are sharing the forecast with the Mumbai Municipal Corporation and they are specifically thanking us. They thanked us saying that that is really really very useful. They found it extremely useful. So what we did last time, we have near real-time AI/ML based forecast 3 days in advance. We have created water logging alert. We have installed sensors. We have used the tweets and we have created an app so that Mumbaikars can report whatever the regions which are getting waterlogged and immediately it will be visible in the portal. And this is what we did. Sure, wait to yeah. So if you look at it, sorry. So if you look at it, this was the app and web portal which was developed, and you can see this is the first page. Every day it will see the rainfall forecast for next day, and for next 3 days forecast it will give, and also it will tell us that for the entire season how did we perform. So this will tell us the entire season's performance. You can click on any station, it will give you for that station, and this will give you every 15 minutes what are the rainfall values. And then, sorry for some of the background noise, but I can't help with this. And then, this is where the people can actually give information about the water levels. So they can click on their location, they can write their name, they can give their height, and they can give some qualitative information. As soon as they provide this information, this will be available in the map where others can see. And these are the app which we have developed. They can do the same thing in the app as well. And yeah. And also there are monitoring stations where real-time data will be available for different sensors and so on. So this is what we did. And last year we got actually, a lot of good feedback. For example, out of one, two, three, out of 6 or 7 extreme days, except one, all of them we have correctly forecasted. Specifically, the last one, where most of the meteorological forecast failed, we did it correctly. Then on that day, because it was an extreme rainfall, we kept on providing the information what are the rail stations which are under stress. And also, a lot of people have appreciated this. And this was the performance over S-word, which is over IIT Bombay, where the rainfall forecast happened. Now, if you are looking at plan for 2025, what Pooja did is that, because what we have understood from BMC is that we are more interested in 3-hourly rainfall forecast. And this is what we started, because initially we did not have radar data, but with GFS we started working on it. And what we did is that we have, because our target is to get extremes, in the loss function for extremes we have put higher weightage, and normal thing we have considered simple weightage, and we have used some convolution as LSTM, where CNN is used for taking care of the spatial pattern and LSTM is used for taking care of memory, and then we have produced. And what we have found is that some of the extremes we are missing, but mostly we are doing quite well. It's not that bad. And if you look at the improvements, if you consider this is GFS and this is weighted LSTM, and what you can see is that huge improvement in terms of R, reduction in terms of RMSE, heat rate you can see less than 0.1 to 0.5 we could get for 3-hourly forecast. False alarm we could reduce, and threat score also we could reduce. So thanks to Pooja for developing such a nice model for 3-hourly. It's working quite well. And you can see with respect to GFS how much improvement, 600% of improvement we could see. You could see, so which is significant. So you can see that with use of machine learning has helped in regional modeling and further improving the results. Now at the same time, one of our student Akshay Sunil is also trying to develop some model for radar nowcasting, where UNet kind of model is used. And the idea here is that for next 1.5 hours, can you take past radar data and see that how the rain band is moving in terms of reflectivity. Then that's what it is being done. And we are working on with IMD so that we can further make it operationalized. Now coming to the flood model setup. So this is also Pooja is working. So Pooja is setting up Q-flow model for the entire Mumbai, and we are showing it for one of the catchment for which we could get some data. And when we applied this model, so you can look at it, in what way the floods are getting developed. The stars are essentially BMC hotspots of flood. And you can see the floods are getting developed with the increase in rainfall. And these are some of the regions which were flooded on one of the day in 2023, and you can see this is this is blue lines are the rainfall and the red line is the flood. In what way the flood depth has increased over Nanachok region, which is one of the BMC hotspot, Mumbai Municipal Corporation hotspot, and you can see the way it is working. So this is working for one of the catchment. You can see how the flooding has increased on that specific day. The important part is that if we have this kind of information, maybe we can think of some foundation model for urban flooding. If we have For a few catchment, can you upscale it over other regions and so on and so forth. So that is the idea of which we are also working. Yeah. And then we verified because there was no very proper verification which were available. So what we did is that we look at the newspaper and we verified. We found that yes, the flood model is actually working quite well. So the idea here is that, I'll end with this one. What we'd like to mention is that we have to get real-time data of satellite, radar, sensor, crowdsourced data, and we should use the static data. We have to merge them together. Maybe you have to use physics-guided ML and come up with urban flood forecasting system, which is a real challenge. But I believe that with the enormous progress that we have made, the machine learning community have made, the climate community have made, it is possible to provide very good solution to the people. Thank you. Thank you for your attention.
Thank you, Professor Subimal, for that wonderful talk about so many different applications or climate of the climate services, from the agricultural domain to the urban flood forecasting system. And like, it was nice to know the work of Pooja, who is sitting here. So the floor is now open to questions. Everyone in sleepy mode after lunch?
Or they want to ask the question to Pooja because they know it very well that Pooja can answer it better than me. Or Usman can answer agricultural questions better than me.
Okay, I am going to read out some questions from the online participants. Uh, so Manoranjan Ghosh is asking, how do you, like, with reference to the this agricultural crop production part, how did you calculate the protein, iron, zinc, etc. increase?
So essentially, you can actually simulate the crop yield. Once you have the crop yield, you know that specific crop, if you have, per unit crop produces this much of this much of protein, this much of iron, this much of zinc they have. It's just a multiplication. Very simple approach.
So basically, for this you use some crop simulation model, is it?
Yes, yes, yes.
Okay. And then next question from Moti Gupta. In agriculture, did you use SMAP soil
Yes, SMAP soil moisture. Yes, it was used and it was downscale. We are trying to even thinking of further downscaling, which our student Usman is working. Usman is there, so Usman is working on this.
Okay. And another continuation of that question, what is your opinion of effectiveness of surface soil moisture derived from Sentinel-1, and what are the best soil and evapotranspiration products available for India?
There is nothing best, unfortunately, because there is such a huge spatial variability, and most of the cases satellite products are unable to really take care of that because human contribution is important. And if you go from one small farm to another small farm, the practices are different, everything is different. So the idea here is that if you can get some sense of soil moisture at surface level, but finally, you have to downscale with in situ data or qualitative information from the farmers. And the real challenge is that how to really merge them together to come up with farm scale soil moisture. So that's a real challenging science question. And Usman is working on it. We hope that some will come up with some answer. Usman will give us some answer in a year time or so.
Uh, okay, a question from Ankita Singh. How using hybrid deep learning models improve the daily extreme rainfall predictions like CNN LSTM over a single deep learning model like CNN? That is how the like basically she's asking how the adding the
No,
LSTM.
for daily exchange, we have not used CNN and STM. So we have used CNN, but what we did further tuning with just for extreme days, with a few extreme days. This is what we have done. So CNN and STM was used for 3 hourly rainfall forecast, and there it was working because just CNN was not working very well for 3 hourly scale because their memory plays some role.
Okay. One more question. What kind of physics constraints could be included in the irrigation management based models?
Uh, Irrigation management model was not essentially there is an optimization model which is used, but if you are considering the eco-hydrological model, which is a physics based model, so essentially it was not a machine learning model, it's a simulation model is based on physics, and outer loop in the in the envelope there was an optimization model, inside there was a simulation model.
Okay. Uh,
Hence.
I had one question. So, like you mentioned that, like in the in the agricultural management part, you mentioned that you are developing the various rainfall scenarios from the forecasts, like using these weather generator kind of things. So, I just wanted to understand what was the role played by those scenarios. I mean, you generated those scenarios, and then how did you use it?
Yeah, so idea here is that if you use just a forecast into the optimization, it is a single ensemble. But what we want is that we want a probabilistic information to be fed into the optimization. And we wanted to use a stochastic optimization. We wanted to give the constant that probability that the root zone soil moisture will be greater than certain threshold. And if you have to do that, you need the ensembles. So what we did is that given a forecast, what is the probabilistic distribution of observations? We tried to get that from the past. And let's say now tomorrow's forecast is available. We know that given this forecast, what are the possibility of observations? And from there, we generate realization and use it in the simulation model in terms of Monte Carlo simulation. And that is inside the optimization model. That's the way we develop.
Okay, okay. Any other question from anyone? Okay, if not, let's thank Shuvimalda for his wonderful talk and the work that he's doing.
Thank you. Thanks, Adway. Thanks for the opportunity.
Yeah,
And
thank.
thanks to Pooja and Usman who are doing excellent work on this.
Yeah, so yeah, we'd have liked to have you in person today, but
Yeah, we had, of course, Pooja and Usman knows that, suddenly a lot of things have come, and because of which I had to stay back at institute. Sorry about that.
okay, okay.
Apologies.
Yeah, no problem. Okay then.